Suppose we have a line, two endpoints labeled D, a center labeled A, the left half of the segment labeled C, and the right half of the segment labeled B. The corresponding letters mean A, random, B, probabilistic, C, chaotic, and D, deterministic. You can see, when starting with a deterministic system, as the amount of information increases, the chaotic features of that system will increase until it's so chaotic that you might as well call it random. However, when you're starting with a random system and you find more information about that probabilistically, you become more deterministic, and therefore you decrease the entropy. So from D to A and C, the entropy is increasing with the information increasing. But from A to D, or during B, the probabilistic section, as the information increases, the entropy decreases. This is what it looks like graphically when plotting information with respect to entropy, where randomness is the middle, the center point. And these can be extremes, like two infinities. So this isn't really an endpoint, it's more of an approaching infinity, and then this is the maximum randomness. Here's a different way of drawing it, where you can see it's circular. Deterministic goes to random, and then back to deterministic. And for deterministic, as the information increases, it becomes closer to random. But for random, as the information increases, it becomes more deterministic. And the distance between the brown line and the black line is how much entropy there is. So determinism, when something's completely deterministic, there's zero entropy. When something is completely random, there is maximum entropy. So this should be like infinitely away from the random. I just added a counterclockwise arrow to show the direction of information increase. Direction of information increase is always in this direction. One last thing, as the space between the brown and black line gets bigger, so as the entropy increases, the more likely you are to use computational or stochastic methods, like non-analytical methods. However, down here, you'd be wasting resources and time. Or you'd be wasting resources because you can definitely use an analytical method to solve the system. But still, sometimes you'll need stochastic methods. And here's like a little summary or something. What?